What did you say, Valeria?
I said that there was no sound online, but now there
Yes,
is.
no, but
Yeah,
it was sound.
We'll be there in 30
Thank
seconds.
you.
Okay, next up we have Evan Patterson talking to us about structured and decorated cospans from the viewpoint of double category theory.
Yeah. Thanks, David. Right, so in this talk, I tried to take another look at structured and decorated cospans, which are now a standard tool in this community from the viewpoint of double categories. There are a few new results, but the main thrust of this work was to try to hopefully simplify and streamline the theory and understand it in a new way. So as you probably know, there's now a quite well-established tradition of modeling open systems as cospans of some kind. So this idea goes back at least 25 years, maybe longer. And the basic idea is that we think of the apex of the cospan as representing a system, and the feet of the cospan as representing the boundary or the interface of that system by which it can interact with others. And in practice, it's usually the case that the system somehow has more structure or is more complicated than its boundary. And so you don't just work with arbitrary cospans, you try to model this extra stuff going on at the apex, and there are sort of two complementary approaches one could imagine taking to that. You could start out in a category with a lot of structure somehow, and then try to restrict what's going on at the feet, and that leads to the idea of structured cospans. Or you could try to start with cospans in some simple sort of category and add extra data to the apex, and that leads to the idea of decorated cospans. So I want to walk through a little bit of the sort of evolution of the ways that people have tried to model open systems as some kind of categorical structure built out of cospans. This is not like strictly following the historical order, actually, but like this is sort of some kind of progression one could imagine going through. So the most naive thing to do is to say, well, I'm going to make my cospans be the morphisms of a category, right? So if I start with any category S that has pushouts, I can make a new category of cospans in S where the objects are the objects of S, and the morphisms are cospans in S up to isomorphism of cospans. And the way cospans compose is by pushout in S. So you've probably seen this before. There are a couple issues. This is nice and simple, but there are a couple issues with it. So in software implementation, we are not working with a whole isomorphism class. We're working with a representative of the class. So it's a little bit unfaithful to what people would actually be sort of doing in a computational setting. But even if that's not the sort of thing that concerns you too much, there's sort of a deeper problem here, which is that systems should have morphisms between them. That's sort of central to the category theoretic viewpoint. But if you're only working in a setup where in a category where the systems, open systems are morphisms, then what happened to the morphisms between systems? Okay, so the most traditional way that you would solve this sort of problem is to move up a dimension, to move to a two-dimensional categorical structure for which the default notion is a bicategory. So the sort of model or prototype of this sort of situation, as far as open systems is concerned, is the bicategory of cospans, where again you have objects and cospans as the objects and morphisms of this bicategory, but now you have as two cells maps between the apexes of two cospans that have the same feet. such that the triangles that you would expect commute. And this does solve both of the problems mentioned before. So you no longer have to consider systems up to isomorphism, and also you've recovered some notion of map between your systems. That seems good. But there are further difficulties. So in all the study of open systems, people have some kind of monoidal structure sitting around, which usually represents a notion of parallel composition or disjoint unions, or basically sticking things next to each other without hooking them together. And if we're just working with categories, this leads to monoidal categories. And although they're not without some complications, we're quite accustomed to working with them in this community. Once you start talking about monoidal bicategories, there's a big jump up in complexity, because you're really dealing with, as far as I understand, a structure that's like basically essentially three-dimensional, and that the way that one would define this in the most general way is as a tri-category with one object. And I don't really know, maybe there is a way, but I don't know really a way of making that definition any simpler. But what's interesting is that if you go to double categories, then you can define a monoidal double category using only two categorical concepts. So you can say that a monoidal double category is a pseudo-monoid in the two category of double categories. And I haven't told you what that latter thing is. We talk a bit more about that later. But the point now is just to convey that like all of these are two-dimensional notions. And moreover, Schulman showed in 2010 that in fact, if you have a monoidal double category, then under some conditions, such as it being an equipment, you can actually generate a monoidal bicategory from that. And so it appears that this is at least as good as a monoidal bicategory. And so people have started using double categories in the field, basically as a kind of technical device to work around some of these challenges of working with monoidal bicategories. And so again, that sort of prototype example for our purposes is the double category of cospans in a category with pushouts. Okay, so the objects and the arrows, or the vertical arrows if you prefer, are the objects in the morphisms of S. And as pro arrows or horizontal arrows, we have cospans in S. And now the cells are maps of cospans in which you not only have a map between the apexes, but between the feet. And you might wonder, what's the big deal? Okay, so we have maps between the feet of the systems. Does this really change a whole lot? And it's not immediately obvious that it does, but it turns out to make a big difference, because double categories fit into a different kind, form the objects of some structure in a different way than bicategories do, and we're going to exploit that. So let's get into a bit about double categories. That was sort of a context, historical sort of overview. So probably maybe you've seen this before in the tutorial or elsewhere. But so the succinct way to define a double category is to say that it's a pseudo category in cats. So what that means is that unlike a category, which has a set of objects and a set of morphisms, we now have a category of objects and a category of morphisms. And the source and target maps are now functors. And then finally, there's a composition and identity, the external composition and identity. And these obey the category laws up to isomorphism, and I won't spell that out, but if you've seen the definition of a weak monoidal category before, then this is very similar. And in fact, monoidal categories are a special case of double categories, as we'll discuss later. Okay, so it's to attach some terminology to this. We think of the objects of the category D naught, that's the category of objects, as the objects of the double category, and the morphisms of D naught as the arrows of the double category. And we think of the objects of D1, that's the category of morphisms, as pro arrows, and finally the morphisms of D1 as the cells of D. And this is sometimes glossed over. It's just like, well, this is how you unpack the definition. This is sort of some like annoying thing you have to think about to find out what a double category is or something like that. But actually there's significance to the fact that the data is arranged in this way. And so the pro arrows of the double category are first and foremost objects, not morphisms. So the slogan that I like to think about here is that pro arrows are objects that just happen to have a source and target can compose. And this is pretty natural from our point of view, because I think open systems are also, they're first and foremost systems or objects. They happen to have boundaries. And so this point, though, is more than just sort of a philosophical one, because it actually fits into how the concepts in the theory of double categories are arranged. And basically, in the most sort of well-behaved notions, that pro arrows are playing the role of objects, not of morphism. So I want to give sort of a first example of this so you get a sense of what I mean if you haven't seen this sort of thing before. So a natural transformation between two double functors, so two structure preserving maps between double categories, this would sometimes be called a vertical natural transformation, consists of basically a natural transformation between the categories of objects and the categories of morphisms in a compatible way, right? So for every objects in D, we have an arrow, and for every pro arrow in D, we have a cell in the codomain double category. And these are both natural, so they're natural with respect to composition of arrows and cells. So what we're seeing here, right, is that the pro arrows are indexing the components of a natural transformation in this definition, right? So they're playing the role of objects in this definition. Okay, and these form the two cells of a quite nice two category. So there's a two category of double categories, double functors, and natural transformations. And so this is that's a fair bit nicer in some ways than the way that you can make a two category out of bicategories. Okay, so we're turning now to some of the main sort of concepts that we'll be working with. So one advantage to having this is that we can formulate in a kind of clean and conceptual way a notion of a co-Cartesian double category. So in this talk, co-Cartesian will always mean has finite coproducts. So you've probably seen that a category with finite coproducts is the same thing as one where you have left adjoints to the diagonal map and to the deletion map. And we can sort of run this same sort of definition in the two category of double categories and say that a co-Cartesian double category is one such that the diagonal double functor and this deletion double functor have left adjoints in this two categories. So that's a nice, clean conceptual definition, which might be contrasted against the much more complicated definition of like a Cartesian or a co-Cartesian, or like a Cartesian bicategory. But what's also nice is that there's a nice concrete description of this, which is quite simple to check in examples. So there's a clean conceptual definition, but also one that you can quite readily check. So it turns out that a double category is co-Cartesian in this sense if both of the underlying categories, the categories of objects and the categories of morphisms, are co-Cartesian. So again, the pro arrows are objects here, and the source and target functors preserve finite coproducts, so they're co-Cartesian. And then the same is true of the external composition and identities. Those preserve finite coproducts. So we're going to use this later. We're going to use this characterization later. Okay. So again, the sort of prototypical example for us of a co-Cartesian double category is in fact the double category of cospans in a category with finite co-limits. So, and using this criterion, it's really easy to see that this works, right? So in the category of objects, which is just X, there's finite coproducts by assumption. In the category of morphisms, so of pro-arrows and of cells, that's a copre-sheaf category on X that indexed by the walking cospan. So that also has finite coproducts, and they're computed pointwise. And then it's clear that the source and target functors, which extract the left and the right foot, preserve coproducts. And finally, the external composition and identities preserve coproducts by sort of the general fact that colimits commute with colimits. So we can see basically almost immediately that we get an example of this kind of object. And as a sort of intuition, we might, given that the double category of cospans is sort of the model system in a will for this theory, we might expect that nice double categories of open systems should be co-Cartesian. And what we're going to see is that double categories of structured cospans are co-Cartesian. So that's where we're going. Okay, so structured cospans are commonly used device in this community that can be used to model all sorts of things, such as open graphs and Petri nets and reaction networks. In our previous talk, James talked about open parameterized dynamical systems. Those are also structured cospans. So what are these? An L-structured cospan where L is a functor from some category A to another category X consists of a pair of objects in A and then a cospan of the form shown. So the feet are the images of A and B under L. So this is sort of restricting. So the notation L is chosen because L is often a left adjoint. So we're thinking that this is sort of restricting the kind of thing you can have at the boundary compared to the apex. Okay, and in their paper on this, Baez and Corser showed that when X has pushouts, you get a double category of L-structured cospans, and then under additional assumptions, you can give this double category the structure of a symmetric monoidal double category. And so the first thing's quite easy, because once you know that cospans form a double category, the L-structured ones compose in the exact same way. They compose by pushout in X. So it's sort of immediate that you get a double category of those, but showing that it has this symmetric monoidal structure is quite a bit more involved and has been given no fewer than 3 proofs in the literature. And all of them involve a fair amount of work. And so the idea in this work is to bypass this by saying, okay, like, rather than giving this monoidal structure, we're going to use the appropriate double categorical universal property and then get the monoidal structure from that for free. Okay, so to elaborate on that, you probably know that if you have a category with finite coproducts, you can make it into a symmetric monoidal category by making a choice of coproducts, and then all the coherence axioms follow from the fundamental universal property of coproducts. And this same sort of thing works for double categories. So I'm going to gloss over this in the interest of time, but basically by abstract nonsense, the same thing works. But actually what I want to emphasize here is that it's good to know you can recover the monoidal structure, but in practice, maybe you just want to work with the co-Cartesian property to begin with, but you can recover the monoidal structure. Okay, so now we're turning to one of the results here. So if you have your category A having finite coproducts and your category X having finite colimits, and then your structuring functor L being any one that preserves finite coproducts, then that is enough for the double category of L-structured cospans to be co-Cartesian. And I want to at least give some indication of the proof, because it's basically simple enough to fit on the slide, and it's part of my thesis here that like this approach is bringing quite a bit of simplicity to the thing. So we can basically again see quite directly that this works. So first of all, the underlying category of objects is A, and it has finite coproducts by assumption. And also by assumption of L preserving finite coproducts, the canonical comparisons from like L of A plus L of B to L of A plus B are isos. And so that means that if we want to form the putative coproduct in this new double category, well, we can start by computing the pointwise coproduct of cospans and then just restrict along the inverses of these comparison maps to get a new cospan that has the right form. And then it follows quite directly that like this does have the right, this has the universal property, and that's it. You get your co-Cartesian double category, and if you want from that, you can pull out a symmetric monodal one. Okay, so turning to decorated cospans. So it is a sad fact of life that not all double categories of open systems are co-Cartesian. So the main example that I have for this is the double category of open dynamical systems. So not with further parameters, but just dynamical systems. There's not enough morphisms in this situation basically to have coproducts. But in situations like this, we can sometimes use the theory of decorated cospans, which is a more elaborate theory, but it does have the advantage of not implicitly assuming co-Cartesianness. So the way that decorated cospans work is that you start with a category A that has finite colimits, and then you have a lax monodal functor from A viewed as a monodal category with the coproduct into cat with its Cartesian product. And given that data, you can construct a double category of F decorated cospans where one of those things consists of a cospan in A, and then along with that, an object in F applied to the apex of that cospan, which we think of as being a kind of decoration. And building on Brendan Fong's work in a more restrictive setting, Baez and Courser and Vasilopoulos showed that there's a symmetric monoidal double functor, symmetric monoidal double category of these things. And a really natural question to ask oneself in this situation, that kind of a common intuition that goes along with the Groton deconstruction, is that it's a thing that sort of attaches decorations to objects. Could you use this to recover decorated cospans in some way? And in order for this, the Groton deconstruction is a thing that decorates objects, but fortunately, as I've been emphasizing, and according to double category theory, the cospans are first and foremost objects, and so one could hope that this would work in a double categorical point of view, and it does. And so this uses a construction due to Crutwell, Lambert, Pronk, and Sizzled, which is the double categorical version of the Groton deconstruction. So there's quite a bit going on in this thing. So this is probably the busiest slide. So I'll just try to talk a bit through the idea of this without going into too much detail. So the data for the double Groton deconstruction is a lax double functor from any old double category A into the double category of spans of categories. And given such a thing, you can construct a new double category, its Groton deconstruction, where, okay, so this is a common sort of theme in double category theory too. How do you do a double categorical construction? Well, you first do it on the category of objects, and then you do it on the category of morphisms, and then moreover, you ensure some sort of compatibility with the external composition and identity. Okay, so to get the category of objects, we take the Groton deconstruction of the underlying functor, F naught, and then to get the functor between the categories of morphisms, we take the Grothendieck construction of the apex categories of those spans. And so in the double category that you get, you have objects which are decorated, and then you also have pro arrows that are decorated in such a way that they're compatible with the decorations on the on their source and targets. And I suppose there's a bit of a typo here because I wrote leg, but we're not doing cospans yet. So this is source and target. Okay, so I got a little ahead of myself. But okay, now we're about to do cospans. So as an immediate consequence of this, if you instantiate this construction for the double category A being a double category of cospans, you get a notion of F-decorated cospans. And it turns out to be more general than the standard one in two ways. First, the decoration can depend on the whole cospan, not just on the apex. And the feet of the cospans also get decorated in a way that's compatible with the decorations on the cospans. And it turns out that one can recover the usual decorated cospans as a special case of this, which in the interest of time, I will pass over. But as you can see from the box here, it's a pretty, you got to string together the right composite of lax double functors, and then you apply this thing and you recover the original decorated cospans. Okay, so I'm going to wrap up now. Sorry, I was a little fast at the end. There are quite a few things from the paper that weren't covered here. So I talk about in the paper how structured cospans also form co-Cartesian equipments or frame bag categories. I talk about maps between structured cospan double categories, and I also talk about some applications of this notion of generalized decorated cospans. So thanks a lot.
Okay, thanks for the great talk, Evan. Questions?
Thanks for the great talk. It's nice to see a clean organization of these many very similar but like subtly different concepts. So I've taken the point of view that a systems theory is a lax double functor from some double category, or these are all monoidal, into spans of set. And I found that you could perform a similar Grothendieck construction to put it into a single double category, but I found I liked having that separation where you separate the interfaces, which here would be like A, and you would have the span separately. So do you think that there's a good reason to stick with actually the structure you used to start? Now that you know you could build decorated cospans, do you think there's a good reason to organize the theorems on the actual domain side of that?
Yeah, that's a great point. I've contemplated that a little bit as well. That it's really nice to know that you can do this, but maybe it's actually enough to just work with this lax double functor. That's what you mean, right? Yeah. Yeah, that makes sense to me on the one hand. I do wonder though, like if you wanted to talk about a particular system, you're going to end up effectively talking about something that is in the Grothendieck construction. So you might get pushed in that direction naturally a bit, but that's an interesting thing to think about.
One more quick question.
You talked about dynam not having enough morphisms,
Yeah.
so it doesn't have coproducts, and then no decorations on the feet in the traditional method. But this method does give you decorations on the feet. Are those related? And if not, like, why would I want decorations on the feet?
I don't know that those things are related, although I haven't thought about it, so I'm not completely sure. But I can maybe give a better answer to your second question of when would you ever want decorations on the feet. The example that I give in the paper is one where there's a pretty common sort of situation in this community where people have some monoidal category, maybe given by generators and relations that they're going to build a string diagram out of. And so it's natural to think that like you have, first of all, a monodal category, and then within that, a particular morphism that has some special significance. And you can arrange those into the pro arrows of a double category via this thing. And in that case, you're going to be decorating you're going to have like cospans of categories, and you're going to be decorating the feet with objects from those categories, and then the apex with a morphism that has those objects, the domain and codomain sort of consistent. So there are, I think, some natural examples where this comes up, and I'm hoping that maybe now that this stuff is available, people will find some other interesting things to do with it.
Great timing. Okay.